when we talk about spherical surface, it is of two types, concave and convex. So right now what I am assuming is that this medium on the left side is rarer and the medium on the right side is denser. In the first place, what are you going to write when you use Snell's law? Okay, so I am using, you would write mu1 sin I equals to mu2 sin r, which is very obvious. Rarer to denser, you can understand this is a concave surface. Hello everyone, today we are learning the spherical refracting surface. Therefore, we are deriving the formula for spherical refracting surface, and it is very important because this is going to be used in deriving the lens maker's formula also. So, if you know the chronology, first we had talked about reflection by plane mirrors, then we talk about reflection by spherical mirrors, then we talk about refraction by plane surface like a glass slab, and now is the turn to talk about refraction due to spherical surfaces. Alright, so now you understand what are we discussing first? Refraction by spherical surface. Alright, so we call it spherical refracting surface. Okay, so now you would say then when we talk about spherical surface, it is of two types, concave and convex. Okay, fine, that's absolutely right. So what kind of a surface is this? If we are, let's say, having the object O here, so you would say it is a convex surface. Okay, so right now what I am assuming is that this medium on the left side is rarer and the medium on the right side is denser. So does that give you an idea that for a convex surface we can have two possibilities, rarer denser or denser rarer? Right now I have assumed that the object is in the rarer medium. Okay, one more thing, that if this is the spherical surface, you draw the radius or the normal to the tangent, and this is where the center of curvature is going to be. Okay, now this is therefore the angle of incidence, because this is the point of incidence and therefore this is the angle of incidence. Okay, one more ray that I have talked about is the ray from the object going in this direction, that will pass without any deviation because it is the case of normal incidence. So the ray is incident normally. Okay, so now if it is going from rarer to denser, it has to bend towards the normal. So this angle here is called the angle of refraction. What are we wanting to derive when we say this formula? So we are wanting to derive the relation between the object distance and the image distance. Okay, so when this ray bends towards the normal, it meets the previous ray here, so therefore this is the image, therefore this is the image. Alright, so object, image and center of curvature. Since it is actually meeting, this is a real image, this is a real image. One more thing, let's call this A, then let's call this as P. We always assume, so you should always mention the assumption. The assumption is that we consider refraction by paraxial rays. So the aperture is always very small and all the angles are very small. Alright, so that is why when we drop a perpendicular here, we can almost take both as the same. So pole P and this normal point P dash are almost going to be the same, thanks to the fact that the aperture is small. Alright, so now let's consider first that this is the let's say angle of, sorry, let's call this angle as alpha. Let's call this angle as alpha. Alright, and similarly this angle as beta and this angle is gamma. So now we are in a state to derive this SRS, that is the spherical refracting surface. Okay, so I and R, alpha, beta and gamma. Okay, so in the first place, what are you going to write when you use Snell's law? Okay, so I am using mu for refractive index, you can use n also. So you would write mu1 sin I equals to mu2 sin r, which is very obvious. Then you will approximately write mu1 I is equals to mu2 r. The reason being angles are very small and then we have the leverage or liberty of writing sine theta as theta. So now is the next thing that we wish to write I and R in terms of alpha, beta and gamma. For that we'll use the exterior angle property. If you look here, then it is going to be I is equals to alpha plus gamma. I is equals to this triangle here, exterior angle I is equal to the sum of interior opposite angles. Similarly, for this one we can write gamma is equals to R plus beta. Gamma is equals to R plus beta, or we may write that R is equals to gamma minus beta. So I've done my homework here. I've written I in terms of alpha, beta, gamma, and I've written R in terms of alpha, beta and gamma. So in the very next step, what I am going to do is I will write I as alpha plus gamma and R as gamma minus beta. All right. Then again, following the same logic, in the very next step, I will write this as tan alpha, tan gamma, then again tan gamma minus tan beta. All right. So this is what I have done. I have replaced, alpha by tan alpha, gamma by tan gamma. Why are we doing that? Because we are wanting to relate perpendicular and the base, because when we relate the base, we are able to relate the distances of the object image from the pole. Okay, very quickly then, what is tan alpha? So you would write AP. So since I can take P and P dash to be the same, so AP upon PO. All right. Then what is tan gamma? AP upon PC. Similarly, what is tan gamma again? AP upon PC minus AP upon PI. So this is what I have done. I've replaced all the quantities in terms of the trigonometric ratio. Now AP is a term that will come common out of the bracket, and same is here, and AP term would cancel out. Now the last part. What is PO? So you would write PO is minus U for obvious reasons, because it is on the left side. Okay. So we always follow the sign convention, right side positive, left side negative. Okay, then PC is going to be plus R. All right. Similarly, that is the radius of curvature, that's why. This is R and this is going to be V. All right. You rearrange this, what are you getting? Mu2 upon V minus mu1 upon U equals to mu2 minus mu1 upon R. This is the formula for SRS, where mu2 means the medium, the refractive index of the medium where the rays are going after refraction, and mu1 is the refractive index of the medium where the rays were before refraction. All right. So this is easy. What you are doing is you are just applying Snell's law, using the fact that sine theta, theta, tan theta all can be written the same, but then the assumption has to be there that the rays are only paraxial, they are closer to the principal axis, and the aperture is very small. So let's look at this formula one more time. Mu2 over V minus mu1 over U equals to mu2 minus mu1 over R, where R is going to be the radius of curvature. So that's something new for us now. We have talked about refraction by plane surfaces. Now we have started talking about refraction by spherical surfaces. This is the build up to understand lenses. That's the surprise, that we are learning this so that we can understand lenses in the upcoming video. All right, I will wait here. You can copy this down and I will talk about the other possibilities also. All right, so now let's take another example. Now this is a concave surface. All right, so this one was a convex surface. So now this is a concave surface. All right, so now I'm assuming that light is going from denser to rarer medium. So again the same thing, but mu1, mu2, so the side where the rays are going after refraction, I'm calling it as mu2, and this is mu1. Okay, So now let's assume that this is the object. As you would know, this is the center of curvature. So this angle is going to be the angle of incidence. Since light is going from denser to rarer, it will bend away from the normal. No surprises here. This is the pole. Okay, even if you extend it like that, this P dash and P can be taken as the same points. Now this angle as usual is alpha. This angle where the rays are meeting after refraction is let's say beta, where the image is formed, and this angle is gamma. So again, very quickly, let's follow the same procedure. First use the exterior angle properties. So I'm going to write gamma is equals to alpha plus I. So using this triangle, I'm writing gamma is equals to alpha plus I. So I will be equal to gamma minus alpha. Similarly, R will be equal to, using this triangle, gamma plus beta. Okay, so this much you can understand. Now applying Snell's law, what am I going to write? That mu1 sine I is equals to mu2 sine R. Again, the same assumptions will carry forward. Mu1 I equals to mu2 R. Okay. Now, I can be written as let's say gamma minus alpha, and R can be written as gamma plus beta. Okay, easy. Now gamma in the very next step, I am following the same procedure, so there is no difference. It's just that I want to cover all the possibilities so that you get any of the derivations, you should be able to derive it. So they might, in the board exam, you might get a particular case when light is going from rarer to denser or denser to rarer, concave, convex, any particular case. So you should be able to handle all of it. Okay, so now this is tan alpha, this is again tan gamma plus tan beta. In the very next step, I will write tan gamma as AP upon PC, then AP upon PO, similarly AP upon PC and AP upon PI. So the factor of AP will again cancel out from both sides, and what are we getting? So instead of PC, I can write minus R because the center of curvature is on the left side now. U is going to be minus U because it is on the left. This is going to be minus R and this is going to be plus V. So when you rearrange this, no surprises for guessing. Okay, so mu2 upon V minus mu1 upon U equals to mu2 minus mu1 upon R. So what I wish to say is that ultimately, if you follow the sign convention, the formula is going to be the same, but the pattern of deriving it is slightly tweaked, is slightly different because of the situation. But I hope you are able to understand that we are getting a real image because the two rays are actually meeting. Okay, so what have I done here? One ray from O, intersecting at point A, as I had said before, bending away from the normal to meet the previous ray or the principal axis at point I. So I is the real image of object O. All right. So that's about this particular case, that is the concave spherical refracting surface, denser to rarer. I will come up with the remaining two also because there are four possibility: concave, convex, rarer, denser, denser, rarer. So there are four permutation combination that you can think of. I will wait, you pause the video, copy this down, then I move forward. All right. So now let's again take the case of concave surface, as you may see here, but it was denser to rarer. Now let's talk about rarer to denser. So rarer to denser, you can understand this is a concave surface. Again, let's call it mu1, let's call it mu2, and this is, let's say, the object. A ray along the principal axis is going undeviated. Another ray from O incident at point A. Angle of incidence is, let's say, I. So this is the center of curvature and this is the normal, as you can clearly see. So the ray is bending towards the normal and this is therefore the angle R. Let's very quickly again do the same thing, that this is going to be the image because the two rays can never meet. So they will virtually meet on the same side as the object, and that is why it's a virtual image, because you don't expect the rays to be here after refraction. They are on the other side. So if you're seeing the image here, that means it's a virtual image. Alright. Alpha, beta and gamma, that's usual now. Okay, so now what do? We apply the exterior angle property. Let's say first in this triangle and write I plus alpha is equals to gamma. Okay, so I've taken the triangle ACO if you want to be precise, then I plus alpha is equals to gamma. Similarly, I can talk about, that if this angle is R, listen to me very carefully here. If this angle is R, then this angle is also R. So I'm going to apply the exterior angle property one more time in ACI, and I'm going to write gamma is equals to R plus beta. All right. So now very quickly, Snell's law, mu1 sin I is equals to mu2 sin R, and then I can write I as sin I as I and sin R as R. Then I can write I as gamma minus alpha, R as gamma minus beta. So that's what I've done. I've written everything in terms of alpha, beta, gamma. The very next step you do understand, tan gamma minus tan alpha is equals to tan gamma minus tan beta. Okay. Now in the very next step, tan gamma can be written as AP upon PC, AP upon PO and AP upon PC. So now this is a little familiar, that's why I'm hurrying up with the process, because it's very monotonous. Now AP upon PI, AP will be common and cancel out, and instead of PC I would write minus R. So all are minus this time, all three are on the left side. PO is minus U, and then PC is minus R, and PI is minus V. So when you rewrite, you get mu2 upon V minus mu1 upon U equals to mu2 minus mu1 upon R. So all the time you're getting the same formula because we are following the sign convention, so you don't get a new formula. For example, for concave mirror, the mirror formula is 1 by V plus 1 by U equals to 1 by F. For convex mirror, it is the same because we follow the sign convention. So ultimately it will give us the correct result. Okay, so this was the case of virtual image. I hope you were able to understand, and I think we can start with the next one now. Okay, but I can step aside, you copy this down, then we move forward. All right, now let's talk about the last case, that is again convex surface, that we have already discussed, but the convex here was rarer to denser. So now we are discussing denser to rarer. So that's the last case possible. Denser, let's call it mu1. So I am not writing mu2 for denser and mu1 for rarer. It's just that ray is starting from the object. I call it mu1. The other side is mu2, even though it can be rarer. So keep that in mind. I am not following the convention where mu2 is always greater than mu1. I am going by the Snell's law, where mu1 is where the ray is starting and mu2 is where the rays are going. Alright, so this is the center of curvature, this is the incident ray. So the angle of incidence is going to be this. Since the ray is going towards the rarer medium, it's going to bend away from the normal, and you don't expect the two rays to meet. Okay, so it's bending fictitiously or virtually in the same side, on the same side as the object. So very quickly, following the same trend, alpha, beta and gamma. All right, and apply exterior angle property. So for this one, I is equals to alpha plus gamma, and for this one, R is equals to beta plus gamma. All right. So mu1 sine I equals to mu2 sine R. In the next step, I am writing sine I as alpha plus gamma and sine R as beta plus gamma. Okay. So, very next step, alpha is replaced by tan alpha, and this point is of course A, needless to say, and this is P dash and P, which we take as the same. So, tan alpha plus tan gamma equals to tan beta plus tan gamma. All right. Now, what is tan alpha? So, tan alpha is going to be AP upon PO, okay, and tan gamma is going to be AP upon PC, okay. Now, tan beta is AP upon PI, and this is going to be AP upon PC one more time. AP will cancel out, and this will become minus U because it is on the left side. This is going to become plus R, it is on the right side. The center of curvature is on the right side, and this is going to be minus V because it is on the left side. It's a virtual image, and this is going to be plus R. Rearranging, you get the same formula, mu2 upon V minus mu1 upon U equals to mu2 minus mu1 upon R. So, no surprises there, the formula is always the same. All right. Mu2 upon V minus mu1 upon U is equals to mu2 minus mu1 upon R. I will move aside, you copy this down, and that is all. So, what I have done in today's class is, given you the derivation of all the 4 possibilities of SRS. I am not discussing magnification like transverse and longitudinal in this one. This was precisely so that you can learn the derivation, you can understand the derivation for all 4 possibility for your board exams. All right. So, in the upcoming videos, we can talk about the magnification and the lens maker's formula and all those things. But this one particularly was for the derivation. But now you understand how SRS formula is, how to apply this. I will come up with a numerical on that, but this is only for the derivation. That's all for this one. See you in the next one. Happy learning. Bye bye.